Hi friends, in this video we are going to see analysis of half wave rectifier. We are going to see some performance parameters of rectifier in order to know how good this is converting AC voltage into a DC voltage. So these are the performance parameters that we are going to see. First is DC or average value of load current, denoted by IDC. Second, the RMS value of load current, denoted as IRMS. Third, output voltage. Obviously, it will be a DC voltage. Next, rectifier efficiency. Next, ripple factor. And peak inverse voltage. Now these are the performance parameters that we are going to learn for all types of rectifiers. So let's see one by one for half wave rectifier. So first is IDC, DC or average value of load current. Since we know the waveform of current is like this. During a positive half cycle of AC supply, I am getting a current waveform, and for negative half cycle it is 0. So if I consider this is a cycle from 0 to 2 pi, only during 0 to pi I am getting a current same as a supply current having a maximum value Im. So this is IO, output current. So I can write over here IO is nothing but Im sin theta, same as the supply current, but that is during 0 to pi, only positive half cycle, otherwise it is 0. So now we have to get DC value, it is nothing but an average value. So IDC is nothing but total time period is 2 pi. So 1 upon 2 pi integral 0 to 2 pi I0 into d theta. Since only during 0 to pi I0 is Im sin theta and otherwise it is 0. So I will consider IDC as 1 upon 2 pi integral 0 to pi Im sin theta d theta. Let's integrate. Integration of sin theta is minus cos theta. I take that minus outside along with Im. So it becomes minus Im upon 2 pi in bracket cos theta, and limits are 0 to pi. Let's apply the limits. So if I apply the limits, I will get IDC equal to minus Im upon 2 pi bracket upper limit is pi and lower limit is 0. Cos pi is minus 1 and cos 0 is 1. So I will get minus Im upon 2 pi in bracket minus 1 minus 1. If I solve, I will get minus Im upon 2 pi in bracket minus 2. 2 I can cancel, minus minus will become plus, and ultimately I will get DC current equal to Im divided by pi. Since Im is a constant, that is the peak value of a supply current, and pi is also a constant, so IDC is a constant value. What does that mean? In a current waveform of output current, there will be a fixed value, it's nothing but Im by pi, which is continuously flowing through load, which we call as DC or average current. Let's go to second parameter, that is RMS current. So it's nothing but a RMS value of load current and given as root of 1 upon 2 pi integral 0 to 2 pi I0 square d theta. As we know, we are getting a output current only during a positive half cycle. So it is root of 1 upon 2 pi 0 to pi. Current will be same as the supply current. So it's Im square sin square theta d theta equal to root of Im square upon 2 pi integral 0 to pi sin square theta d theta. Sin square I can replace as 1 minus cos 2 theta by 2. So if I take a 2 common, I will get root of Im square upon 4 pi and then I will get 1 minus cos 2 theta whose integral is theta minus sin 2 theta upon 2, limits are 0 to pi. So if I apply the limits, I will get IRMS equal to root of Im square upon 4 pi, upper limit is pi, so it's a pi minus sin 2 pi divided by 2, and if I apply the lower limit 0 minus sin 0 divided by 2. As we know, sin 2 pi is 0, sin 0 is also 0, so ultimately this is equal to root of Im square upon 4 pi and bracket I will just get pi. Pi get cancelled, so this is equal to root of Im square divided by 4 and square root if I take, I will get IRMS equal to Im divided by 2. So this is the value of RMS current flowing through load in half wave rectifier. Let's move to the next parameter and that is output voltage Vdc. So as we know, Vdc is nothing but voltage across load resistance and given as IDC multiplied by RL. IDC we have already calculated, and what is that? It is nothing but Im upon pi multiplied by RL. Im is the peak value of a supply current and that is given as peak value of supply voltage divided by total resistance in a circuit. So in a circuit I have Rs, resistance of secondary winding of a transformer, plus Rf, forward resistance of a diode, and RL, load resistor. So I write here once again, in the expression Rs is the resistance of secondary winding of a transformer, Rf is forward resistance of a diode, and RL is the load resistance. So if I compare these values, I will come to know Rs and Rf together is very less than RL. So I can neglect Rs and Rf. So if I do that, I will get Im equal to Vm upon RL. And if I substitute this value in Vdc expression, it will be Vm upon RL upon pi multiplied by RL. So this RL and this RL will get cancelled, and ultimately output DC voltage will be Vm upon pi. Now let us see rectifier efficiency. It is defined as the ratio of DC output power to AC input power. Both these powers are flowing through load resistance only, but here the current will be different. So DC output power will be nothing but IDC square multiplied by RL, and AC input power will be nothing but IRMS square into RL. So if I substitute this, I will get rectifier efficiency as IDC square multiplied by RL divided by IRMS square multiplied by RL. RL I can cancel out. So ultimately it is IDC upon IRMS whole square. And we know IDC is nothing but Im upon pi, and IRMS for half wave rectifier it is Im by 2. So we just substitute these values over here and we will get rectifier efficiency as Im upon pi divided by Im upon 2 whole square. Once again I can cancel this Im, and this will give me finally efficiency as 4 upon pi square, a constant. If I substitute pi as 3.14, I will get efficiency as 0.406. In percentage, it will be 40.6%. So this half wave rectifier is capable to converting AC into DC in 40.6%. It's not that much high. Let's go to next parameter, that is ripple factor. The output that we are getting from half wave rectifier is not a perfect DC. It has some amount of AC along with DC, and that AC content is called as ripple. So we need to filter this out, hence filter circuits are required. So first let's define the ripple. The output of a rectifier is pulsating DC in nature. What is the meaning of pulsating DC? It contains DC as well as AC component, and that AC component is called as ripple. So what is the ripple factor? How much AC component we are having compared to DC, that is called as a ripple factor. So ripple factor is nothing but ratio of RMS value of AC component upon DC component. Now this can be represented as IAC RMS and DC is IDC. Load current I0 is addition of IDC and small IDC, and this small IDC is AC component. But what we should know is RMS value. Hence I can say RMS value of load current will be nothing but root of IDC square plus IAC RMS square. That means root mean square value of this I0 is root of square value of this plus RMS value whose square I have to take. So finally what I will get, IAC RMS is nothing but root of IRMS square minus IDC square. We want ratio of IAC RMS with IDC. So IAC RMS upon IDC will be equal to root of IRMS square minus IDC square divided by IDC. So if I further simplify this, I will get ripple factor is nothing but root of IRMS upon IDC whole square minus 1. We know IRMS is Im upon 2 and IDC as Im upon pi. So if I substitute these values, I will get R equal to root of Im upon 2 divided by Im upon pi whole square minus 1. Again I can cancel and ripple factor will become root of pi square by 4 minus 1. All these terms are constant. If I substitute value of pi, I will get ripple factor equal to 1.21. In percentage, it will be 121% of a DC value. So it is very high ripple is there in case of half wave rectifier output voltage and current. So filter requirement is very high. Next parameter is peak inverse voltage. And that is PIV. The definition of PIV is like this. It is defined as the maximum reverse voltage that can be applied across the diode without damaging it. For half wave rectifier, it is Vm. Let's move to the last performance parameter. Which is also called as TUF. So, TUF is the indication of what is the utilization of a transformer, and that is given as DC power delivered to the load upon AC power rating of a transformer. Now, DC power is PDC and AC power rating is PAC rated. We have calculated PDC as IDC square multiplied by RL, and AC power rating of a transformer will be Vrms multiplied by Irms. Now, Vrms is simply Vm upon root 2, but Irms we have calculated for half wave rectifier as Im upon 2. So, this is very important part, because RMS value of a load current is nothing but a RMS value of current flowing through secondary of a transformer. So, if I substitute this, I will get TUF as IDC square multiplied by RL upon Vm divided by root 2 multiplied by Im upon 2. Now, Vm is the maximum value of voltage, can be given as maximum value of current multiplied by RL. I am neglecting RF and RS, which are forward resistance of diode and resistance of secondary of a transformer respectively. And for IDC, I can substitute Im upon pi. So, if I do this substitution, TUF equal to Im upon pi the whole square multiplied by RL, and Vm will be Im multiplied by RL divided by root 2 multiplied by Im upon 2. So, that will give me, if I cancel this RL, and here is Im square upon pi square divided by Im square upon 2 root 2. Again I can cancel Im square and Im square. So, transformer utilization factor I will get 2 root 2 upon pi square. All these are the constant. If I put pi equal to 3.14, ultimately transformer utilization factor for half wave rectifier I will get 0.287 or 28.7%. So, here we have seen all performance parameters of half wave rectifier. Thank you.